The control of biomolecular interactions on electronically conducting surfaces underpins our ability to develop novel platforms for protein separations, biosensors, and biomedical implants. Our foray into this area dates back over 20 years and involved the use of affinity chromatography phases, wherein we use conducting polymer components containing a protein, human serum albumin. Our intention was to explore ways to control the interactions of that protein with the corresponding antibody, anti-human serum albumin. The antibody trapped on the column via the interaction with the human serum albumin protein was subsequently eluted and quantified by measuring the units of activity. With no potential applied to the column during the trapping step, 2,366 units of antibody activity were recovered. With the positive potential applied to the column during the antibody trapping step, the amount recovered increased. When a negative potential was applied during the trapping step, then the amount of antibody recovered decreased. This experiment indicated to us that even complex biomolecular interactions can be controlled using the conducting polymer host matrix combined with electrical stimulation. In subsequent experiments, we turned our attention to the control of antibody-antigen interactions on surfaces to be used for biosensing applications. Here, the antibody is incorporated into the conducting polymer at the point of synthesis. Now we use electrical stimulation to assist in antibody-antigen binding. We found that if the electrical impulse is reversed quickly enough, we can even effect a reversible protein binding interaction. This has subsequently been used for the development of a number of novel biosensing platforms. By far our most sophisticated measurements and our most exciting demonstration of the ability to control biomolecular interactions using conducting polymers has been achieved using bioatomic force microscopy. Atomic force microscopy provides nanodomain resolution even when operated in water, an environment that is biologically relevant. Recently, protocols that allow us to attach specific biomolecules to these probes have been developed. We then utilize atomic force spectroscopy to measure forces required to pull that molecule off novel surfaces. This provides unprecedented quantitative data on these critical biomolecular interactions. We can bring the molecule of interest into contact with an organic conducting polymer surface, and then apply different electrical potentials. Here we see that on changing the electrical potential, the force required to remove the biomolecule of interest is greatly affected. Over the past 2 decades, using various experimental approaches, we have gained insights into our ability to control complex biomolecular interactions using conducting polymers. We will continue to refine these experimental approaches, and as we obtain more detailed knowledge, this will impact on the development of novel protein separation systems. This unprecedented level of control over biomolecular interactions provides new platforms for the development of new biosensing technologies and new materials for medical bionic devices.